understanding the material science aspect of sensors. That's what we're working on. So one of my area is development of nanoparticle-based metal and metal oxide gas sensors, which are not what we're proposing is some slightly new concept, and that's what I'm going to discuss. So, although in the original plan, I think I wanted to discuss for semiconductor optical fiber-based sensor, but that was based on the work which 2 or 3 of my colleagues in the development department are doing. But later on, I decided I will speak on what I am doing. And so this is the first part of the lecture, metal and semiconductor nanoparticle-based resistive gas sensors. They are based on measurement of the electrical changes in the properties of the material when it is exposed to a particular gas. Then one of my colleagues, Professor Billy Gupta, is working on optical fiber-based gas sensors. It's slightly similar. Here the semiconductor layer is deposited onto the optical fiber, and the gas interacts with the metal oxide, changes its electric properties, and that in fact changes the properties of the light which is transmitted through the optical fiber, and that's what it senses. So this is optical sensor, but it is detecting the same gas. The first type is the sensing parameter is the change in the electrical property. And we also have Dr. V.S. Mehta. He is working on laser scattering based particle sensors. So combined, what we are proposing is that a combination of these three can be used to make a air quality sensor. Imaging is which we will not be importing from China, or we will not be purchasing, but we will be fabricating here itself. I think this is also something which requires very high technology and keeping in tune with the driving force of the government that make in India. That does not mean that we buy sensors from outside and then we develop. Okay, that's a part of it. That also has a particular, that development also has to be taken, but we must do that development using the sensor which we develop. So this is high technology. Okay. So what I'm going to show you is some of the work which we have done in this area. And you have to bear with me because this will have a lot of some sort of material science, chemistry and physics. And less on sensor, less on this air quality monitoring. So these are some of my other areas, but I will not bother you with that. Resistive sensor, I will just like to give you a quick introduction of what is a resistive sensor. Resistive sensor is a semiconductor layer, and you take 2 electrical connections because we have to measure electrical resistance of the sensor. And when the sensor is exposed to, so this is a typical sensor, when it is exposed to and these are the 2 electrical connections, and you are measuring the electrical resistance, basically you verify some voltage and measure current, and this is what you can see that when it is exposed to a particular gas, this is what we call it a switch on cycle. You switch on the gas, there is change in the electrical property. Electrical resistance can increase or electrical resistance can decrease. There are some oxides, especially these are called N-type dope, these are doped with more electrons. The electrical resistance changes in one direction, it is doped with another type, P-type semiconductor, there is decrease in the electrical resistance on exposure to the sensing gas. So all the time what we are doing is we are exposing these sensors. Let's say the example which I will take will be the hydrogen sensor, where you expose the gas first to the sensor to the hydrogen, and then you switch on and this hydrogen is not pure hydrogen, this is a fixed quantity of hydrogen in air. Okay? So similar to, because you are trying to simulate the real conditions, and when you switch off this gas, then you switch on the air. So all the time you are switching on and switching off between air plus your sensing gas and air. So this is one time, so you are switching off and then you are. So this ratio, as defined here, this is the international definition of sensing response. What is the resistance in sensing gas minus the resistance in air divided? So sensitivity has to be high. So that's what we say, the sensor should have high sensitivity. That means this change should be high. But in fact, even more important than the sensitivity is this response time. How much time, when you switch on the gas, how much time the sensor takes to go from, let's say, from this point, which is a resistance in the air, to this point where it gets a saturation, and it's a resistance in the sensing gas. The normal definition information is the time taken by the sensor to reach 90% of the saturation value. And same way is the recovery time. The sensing response, sensing time and the recovery time also has to be slow, so the sensor has to be available for the next cycle. So this is also very important. But the most important parameters for oxide sensor, which we're talking about, which are very commonly used for environment sensing, is the drift in the sensing response. That the sensor, the sensitivity remains same, but all the time is quiet, it does not come back to this point. As you do, the sensor goes to 100 cycles, it keeps on going slightly shifting in one direction. This is one of the very nagging problems in sensor. The practical sensor people who prepare them in the laboratory or in the factory, they are faced with this drift in the sensing response. Many times, people try to correct this using an electronic circuit, but that's not a good option. One should have, you have to understand the physics and chemistry of the sensor to arrest the drift of the sensing response. This is very, very important parameter, and most of the time, the oxide-based sensors are all good properties, and this drift is one of the nagging issues in oxide sensors. Temperature of operation is important. What sensor, what temperature to operate. It's based on the chemistry of the process, because you have carbon monoxide or NOx or whatever it is, it's coming and it is reacting at the semiconductor surface. Both in the resistive sensor and optical fiber sensor, it has to react. What is the temperature at which this chemical reaction is taking place? And then when the gas is switched off, then the gas has to go back. And so it has to be a reversible reaction. And what is the temperature at which this reaction will take place? So people who understand the chemistry and physics of the sensing material, we are trying to, all the time what we are trying to do is modifying the material properties so that the sensing operation can take place at room temperature. You can understand when you have to make a system out of it. If each time the sensor has to be increased to 200 or 300, most of the oxide-based sensor operate in 200 to 300 temperature range. So there is a lot of research is needed, and we are doing that kind of research to decrease the temperature of operation. What temperature we operate. Stability is very important, and stability, both material and device stability is important. Sometimes the material, there are changes in the material properties, and sometimes the device itself gets deteriorated. So these are some of the research issues, and it should be a carrying out work in different directions. And maybe I'll just demonstrate you by taking the first part of the lecture. I'll spend on hydrogen sensor, because we in fact have last 10-15 years we've done a lot of work on hydrogen sensors. I will want to show it. And it also shows all the problems and the issues which I just mentioned, right? So what we are going to speak on three types of issues. One is working on nanoparticle-based sensors. Synthesis of size-selective metal and oxide. Synthesis of size-selective, I think from chemistry and physics point of view. Size-selective means that you're making nanoparticles. Nanoparticles are very good for sensing because they have very large surface area. The surface area, that is the percentage of atoms which are there on the surface per unit mass or volume of the material is extremely large. As you go to smaller size, this specific surface area per unit volume is proportional to 1 by r. As the diameter decreases, this decreases. And all the time sensing gas is going to interact at the semiconductor surface. You increase the surface, you increase the sensitivity. That's why people want to make nanoparticle-based sensors with smaller particle size. But when really fabricated, it is important to control the size. That's important. Controlling the size, that means I should be able to prepare sensors with 5 nanometer particle size or 10 nanometer particle size and 50 nanometer. With 10 nanometer size, and then I'm preparing what is the distribution. That's very important. Okay, especially because when you really want to solve these problems, you have to understand the physical, electronic, and chemical processes. You must understand them from how they change as a function of the size, so then you must have a control on the size. So I will show you a method which we have at IIT Delhi, where we can prepare metal and metal oxide, like tin oxide, indium oxide nanoparticles of very, very controlled size. In fact, what I will show you is that when you prepare them, there is no distribution. They are all of the same size. Okay? And this is very, very important. Then I will give you an example of using this technique, palladium nanoparticle-based sensors, and then we will go to the next generation sensor, which are based on palladium nanoparticle graphene component. Graphene is another material I think many of you might be knowing. Graphene, the important thing from sensor point of view is all the atoms of graphene are 100% surface atoms. All the atoms are on the surface, and they are available for reaction with the sensing gas. This is one of the very important material from sensing point of view. That is why we want to make composites of the material along with graphene and choose it to improve the sensitivity and safety. And I will show you that we have now developed a new type of sensor which we call as an interface sensor. And I will show you that what are the advantages of the sensor. So let's go to the first part of this chart, comparing of site-selected nanoparticles. So this is our method of preparation. We call it as the integrated gas-based sensor method. Integrated because it is integrating two or three technologies. One is the material group technology with size selection. I know many of you might be already aware of differential mobility analyzer. This in fact is also used to detect the particles in air, but we are not using it for that purpose. We are using here to control the size of the particles which we are going to observe in the laboratory, nanoparticles. So this DMA, there is some change in the design. We have to modify it because the DMA which is used, which is commercially available for air quality monitoring, works in the micron range. And here we have to control the size in the nanometer range. So some modification, the design has to be done. So that has been done. So this is what we do here is we prepare first the material. This is a spark limiter. Let's say we are making hydrogen sensor based on palladium. So these are two rods of palladium, and there's an electric spark between them. Due to this electric spark, atoms of palladium start coming out from this palladium rods, and they go to the vapor phase, where they collide with each other, and what we call, so we are using spark generator, but there are different methods in one demonstration. Then these palladium atoms, the carrier gas takes these palladium atoms to another device with charge these palladium particles. And these charged palladium particles then go inside the differential mobility analyzer, where they are selected according to their electrical mobility in the carrier gas, which is the velocity per unit electric field. And this velocity is inversely proportional